We are here to help.
A linear differential equation is an equation of the following form, where the coefficients a sub n of x and r of x are arbitrary differentiable functions of x only. These functions do not need to be linear in x, but cannot contain any y's. Linear equations differ in order and in types of coefficients a sub n of x. In this video, we will be discussing different types of linear differential equations and what methods are used to solve them. First-order linear differential equations. A first-order linear differential equation has the following general form. In order to begin to solve a first-order linear differential equation, we need to first rearrange it into standard form by dividing everything by y prime's coefficient and moving the y terms all to one side. Once our equation is in standard form, we can begin to solve. First-order linear differential equations are solved using an integrating factor. Every first-order linear differential equation uses the same general integrating factor of e to the integral of p of x dx. Note that if q of x equals 0, then our first-order linear differential equation can be solved using separation of variables. Second-order linear differential equations. There are a few different types of differential equations that fall under this category. We will begin with homogeneous with constant coefficients. A second-order linear homogeneous differential equation with constant coefficients has the following general form, where a, b, and c are constants and a is not equal to 0. To solve this type of differential equation, we start by solving the characteristic polynomial. There are three different scenarios that can arise from solving the characteristic polynomial, each of which results in a different solution. If the characteristic polynomial has two distinct real roots, then the solution to the differential equation has the following form, where c1 and c2 are constants. If the characteristic polynomial has one repeated real root, then the solution is the following. If the characteristic polynomial has complex roots, then the solution is the following. Now let's look at non-homogeneous with constant coefficients. A second-order linear differential equation with constant coefficients has the following general form. Since this is non-homogeneous, r of x is not 0. There are two methods that can be used to solve a differential equation of this type. Determining which method is best suited depends on the coefficients. The first method is called Undetermined Coefficients. This method is only used in particular circumstances. We first need to rearrange our differential equation in the following form. G of x is the function we get from moving r of x over the equal sign. We use undetermined coefficients if g of x is any of the following: a polynomial function, an exponential function, a sine or cosine function, or a sum, difference, or product of either of the above three. We use the method of variation of parameters when g of x isn't in any of these forms. However, this doesn't mean that you can't use variation of parameters to solve these types of equations. It may just take longer. Second-order linear differential equations with non-constant coefficients are not easy to solve, regardless whether they are homogeneous or not. There are many variations of this type of differential equation, but there are some which, when recognized, are easily solvable. A Cauchy-Euler or Euler equation has the following form. There are two methods to solving this type of equation. The first is to use a predetermined solution of the form x to the power of r, where r is an unknown power. If we substitute this into the equation, we end up with a quadratic in r, which becomes our characteristic polynomial. We can also make a change of variables for x as e to the power of t, to end up with a second-order linear differential equation with constant coefficients. The characteristic polynomial we obtain from this is the same one we obtained before. Regardless of the method we use, there are three different solutions that can arise from the characteristic polynomial. If we have two distinct real roots, if we have repeated real roots, or if we have complex roots. If the linear second-order differential equation is missing the y term, we can make a simple substitution for y prime and turn it into a first-order linear differential equation. We solve this using the integrating factor mentioned earlier. We can also check to see if our equation is exact. A second-order linear differential equation is exact if and only if the following conditions hold. If this equation is satisfied, then our differential equation is equal to the following, which, if we integrate both sides, transforms into a linear first-order differential equation which we know how to solve. Although these types of linear differential equations have particular solution methods, there are other methods that can also be used. These include Laplace transforms, series solutions, and reduction of order. These methods can be used on higher order linear differential equations as well as second order.